Module 6, Section 4, final section, and we're talking about DC motors. Okay, for a start, what is a motor? A motor is anything that turns electrical energy into motion. So my fan's up above me, they've got motors in them. My phone, when it vibrates, it has a motor that lets it vibrate. An electric car, like a Tesla, it will have a motor in it, an electrical motor. So how does a DC motor work? Well, let's look at what its components are. Okay, if I have a DC motor, there are some parts that move and some parts that don't. So the moving parts consist of what's called a split ring commutator. That is a ring of metal which is split so that the two halves of it don't touch each other. Those are connected to a coil of wire, usually multiple coils, but we're trying to do the simplest DC motor possible. And those are all the parts that move. Then the parts that don't move are the source of magnetic field. So it could be some bar magnets on either side, north and south, creating a pretty consistent magnetic field going from north to south across there. Some brushes, and the brushes touch the moving parts. So the brushes are still, the moving part moves past them, so they brush against the moving part, hence the name brushes. And then a DC power supply, because we've got a DC motor here on our hands. Now, how does it actually work? How does it produce a turning force, a torque? Well, we have a source of current, right? We've got our positive terminal, our negative terminal. Current is going to travel from the positive through the brush into the commutator, around this coil going up, around, going down over here, back into this brush into the negative terminal. We have current. We have it going inside a magnetic field, looking at this side here on the left. Okay, so we get a force going into the page at this spot here. So here force is into the page, I'll say into here. Okay, so you can probably guess if we flip the direction of current over here, we have magnetic field going across, we have current going down. So now my force is out of the page away from my computer. So here the force is out. And so you can imagine if you're looking at this whole thing from this side, you can see that this side's coming up, this side's going in. So the whole thing spins kind of anti-clockwise if your eyeball's here looking at it from that direction. Now, what are the functions of its, and that's how it spins. So what are the functions of its components? Well, the magnets, the power supply, the coil of wire, that's really just creating this force in the first place, right? We need the current in the wire, we need the magnetic field, that's creating our force. The only parts left are these brushes and the split ring commutator. They're a bit tougher to understand. To understand them, we kind of need a moving picture. I'm going to try and draw a few frames of it to help you understand. We need to think about one side of this in sort of a green color. There we go. Right, half of it's in green. And the green half right now is connected to the negative terminal. So you can imagine that when it's turning, eventually it's going to be completely vertical like this. At that point here, we've got the green part's going to be on top, right? It's this circle here is spinning around, and now the green half of the commutator is on top. Okay, it's on top, and it's got the coil coming up. Can't draw this very well, but yeah, let's just say it goes across like that, down. We've got the blue coil going down. It's coming across down here, and it's connected to the blue half going across like that. At this spot here, the brushes aren't really connected to anything. The brushes are touching where the split is. Yeah. This one's kind of useful. So you can see, you might even be able to see where we're going here, right? At this point, there's no current because the brush is touching the gaps. And before we had this green one on the side, the green one was touching the negative terminal. It's now spun up, and you can see if this keeps spinning down, it's going to touch over to the positive terminal over there. So let's imagine that happens now. So it's spun around the whole way. Now it's touching the positive terminal on this side. I'm going to try and draw this a bit faster. Boom. Now the blue side is touching the negative terminal over here. Okay, and we've had a complete flip. Now you might think that flipping them around might flip the direction of force, but it actually does the opposite. Okay, because now on this side, this is the positive terminal. Positive goes up here. We've got our direction of current up there, direction of current down there, boom, into the negative terminal here. Okay, this, if we look at it from this direction and we think about where our magnetic field, it's going to turn in that same anti-clockwise direction that it did here. If you imagined that the negative terminal was stuck to the green side, and then as the green side flipped across, it was still attached to negative. In that case, our current would be going the opposite direction and it would spin in the opposite direction, which would be no good. Our motor would be kind of flipping back and forth instead of giving us continual motion. Okay, so this split ring commutator is a really good design that helps us flip the direction of current every half turn. Really cool. So that's all the functions of components. Now let's look quantitatively at the torque that we get using this equation here, right? Now we already know a lot about the force produced here, right? Because we've looked at the right-hand rule, the motor effect, and the amount of force there. And we had an equation that said the amount of force was equal to Bill, was equal to magnetic field times current times the length times sine theta. Sine theta, Bill sine theta, okay? And that's the same force that's here into the page and here out of the page. Okay, so we can, there's two lots of it here. In this case, B, the magnetic field, that's the magnetic field strength of these magnets here. I, the current, that's the current coming from this power supply, and L, the length. The length is going to be, let's do it in orange length. That's going to be the length of wire here. It's the wire in the magnetic field. If you think about the current across here, that current is in the same direction as the magnetic field, no force there. So we don't worry about that one. All right, now there's two lots of them. So the force in our motor here is going to be equal to 2 times BIL sine theta. And remember, theta is going to be the angle between the direction of current and the direction of magnetic field here. So they're at right angles, right? Magnetic field here is coming across like this. That's perpendicular to the direction of current. So sine theta is going to be sine 90 equals 1. Okay, 2 times B times I times L. Now, we're not looking for a force though, we're looking for a torque. And you might remember that if you imagine a bolt being pulled out by a wrench, being turned by a wrench, right? We need to put a torque on the thing. The torque's a combination of the force that you pull down and the length between the pivot point, that's this point here. The pivot point's the middle of the bolt, length between that and the spot where you're putting the force over here as well. So this distance or this length times that torque is equal to force times distance, as long as those two are parallel to each other as well. And you can see that they are. This is a right angle right here. Okay, so in this case, in the case of our thing here in purple, if we are to have a torque, the distance is going to be the distance between the pivot point and it's going to pivot right down the middle here, right? So between the force at the wire and the pivot point, it's going to be this distance along there. Yeah, so if we wanted to change our equation to a torque equation, we have to say that torque is equal to 2BIL, right? That's the force. Torque is equal to force times distance, and we're going to have all of that times the distance as well. Yeah, and let's chuck on the sine theta just to be safe. Now we can simplify this a lot, yeah? Length times distance. What happens if you have a shape, running out of colors to use, let's use this pink. If you have this shape here, right, and you are timesing the length of one side in orange and the distance across the middle here, you get the area of that shape. But we've only got the area of half the shape. But hang on, we have this 2. So if you times this area by 2, you've suddenly got the area of the whole coil. So the 2, the length, the distance, that can all just be simplified to area. And once we do that, we get our final equation. We get torque is equal to the magnetic field strength times the current, and then we have 2 length distance, which all is area, and then that times sine theta. Beautiful, isn't it? That's what we've got over here. Oh, there's an n as well. N just means every coil you add on top of it just adds the force on again. So if you have 3 coils, you have 3 times as much force, right? We just have 1 coil here, so we just have 1 lot of this force here. Keep in mind now that theta is going to be the angle between the area and the magnetic field. Now, areas have weird vectors. If I have this as an area, the vector is coming out of it like so, right? The vector is perpendicular to the area. Crazy. So the area here, the vector for this area is actually going to be perpendicular to it, so it's going to be going straight into it, and that is perpendicular to the force. So this situation here, where the area is like this and the magnetic field is kind of skimming on top and underneath it, that's your max force. Okay, last thing I have to talk about is back EMF. This is just trying to obey the conservation of energy. So back EMF is admitting that what we've created here is a generator as well. We have coils that are moving in a magnetic field. That means they're experiencing a change in flux. Let's get rid of all of this and all of that. So if we have a change in magnetic flux, that means that we need to have an induced current. So the coils are having an induced current. Does this current go in the same direction as the current we're producing? No, that'd be crazy. If it did, if it added to the current, that'd just make the motor go faster. And the faster would mean there's a bigger change in flux, and the bigger change in flux means we get more current, which needs to go faster. And we'd have a infinite energy machine, and it would explode and form into a black hole. That wouldn't be very good at all. Instead, it works in the opposite direction. So back EMF, some people could consider it the enemy, but really it's just like, friction, entropy, that kind of thing. It's just making sure that energy is conserved, right? And this makes sense. If the torque is equal to, if we have a force on our coil and the force is accelerating the coil, because that's what forces do after all, right? They don't make them travel at a certain constant speed. Forces accelerate. So if it was a constant force, then it would just get faster and faster forever. Thankfully, it's not a constant force, because the faster the coil moves, the more change in flux it experiences, the more current it produces against the supply, slowing it down, eventually keeping it at a constant speed. When the amount of induced current, that's back EMF, is equal to the amount of supply current, that is when we have a motor moving at constant speed. Or in reality, if we think of a graph of the, let's say the current over time, right? The overall current, it's going to start off quite high from the supply, but then as the motor speeds up and back EMF kicks in, that current is going to decrease until it hits a floor, and the current will never hit zero. That's because it always needs some current to overcome resistance, air resistance with the rubbing parts, rubbing with the brushes here. So the supply current is always going to be a little bit higher than the induced current, than the back EMF, but only a little bit. In the end, this creates equal and opposite forces, keeping a constant speed of motor rotation. If you increase the supply current, so you turn up the dial, you increase the supply current, that's going to increase the speed of your motor. As the motor increases in speed, it's going to produce more change in EMF, and that's going to decrease it as well. Now it's going to be constant again, but now it's constant at a higher speed, because at this point here, you increase the current to do that. Okay, I'm done. That's all for motors. We have to talk more about this anyway, 2 dot points time. Bye.